Alright class, today we're going to be talking about the short run behavior of polynomials. I don't have a working computer that will do this, so I'm doing this by hand. The notes say, if you remember from last class, we learned that to predict the long run behavior of a polynomial, we use the highest power term. And that's to determine what's going on at the ends. Today we're going to talk about the short run behavior. And in order to do that, that involves finding the zeros of the polynomial. So in order to find the short run behavior, we actually need to find the zeros of the polynomial. And one way to do that is to factor the polynomial into as many linear factors as possible. So for example, here's a polynomial. Minus 5x plus 6. But that doesn't, I know that the long run behavior, the limit of this function will, as x approaches infinity, will be the same as the limit of x squared as it approaches infinity. But that's the long-term behavior. What's going on in the middle, I call it, in the short run behavior? Well, I can rewrite this in factored form. And as you can see, that gives me an indication about the zeros, because this is a linear factor, and the zero of this linear factor is x equals 3. And the zero of this linear factor is x equals 2. So that tells me about the short-term behavior of this polynomial, is that it has zeros at 3 and 2, or it crosses the x-axis at 3 and 2. So it goes down to a relationship between linear factors and zeros, that if you have a polynomial p that has a linear factor, x minus k, then that means p has a 0 at x equals k, and that's what we found up here. This was a linear factor, x minus 3. In this case, k is 3, so that means that it also has a 0 at 3. Okay? Conversely, if p has a 0 at x equals k, then p has a linear factor of the form x minus k. So that means if someone tells me that p has zeros at let's see, 2, negative 2, and 5, then that means that p has factors, linear factors, x minus 2, x minus negative 2, and x minus 5 as factors, which means I can multiply them together and get a form of p. Okay, this is not the exact form of p, because we may have some coefficients, like this may be 3 or 2 or 1 or whatever the deal may be, but that gives you some idea about the linear factors. So then over here it says the graph of an nth degree polynomial has at most n zeros and turns at most n minus 1 times. So over here we had a 2-degree polynomial. So based off this, it tells us that we have at most 2 zeros, 3 and 2. Now in this case we have exactly 2 zeros, and in this case we have exactly 3 zeros, and this must be a 3rd-degree polynomial. But not always will you have exactly the same number of zeros as the degree, but this promises you that you will have at most that many. In other words, no more than that. And then it says it turns at most n minus 1 turns. So in this case, turns vice versa. So if p is a polynomial with a repeated linear factor, then p has a multiple 0. So what's an example of a repeated linear factor? Let's say this is a linear factor, but then I have x plus 1, and then I have another x minus 3. Well, that's a repeated linear factor of x minus 3. So that means we still have a 0 at 3 and negative 1, but also at 3. Well, these two are the same, so this is just a repeated 0. Now, if the factor occurs an even number of times, then the graph of y of equal px does not cross the x-axis but bounces off. So in this case, the linear factor x minus 3 is repeated 2 times. So that means that if I were to graph the function at that point of 3, it's either going to do something like this, which means bounce off, or it's going to do something like this. Okay? Because the linear factor x minus 3 occurs 2 times, which is an even number of times. if the factor linear factor occurs an odd number of times, then the graph of p of x crosses the x-axis, but it looks kind of flattened over there. So it may be something that looks something like, and I can draw like there as well. Okay, so those are the notes and these are the video. If you have any questions, we look forward to answering them. Email me.